To close out section 2.1, we are going to do one final example of arc length, and it's going to be a really basic example. So in example 6, we're going to let S denote the length of the arc of a circle of radius r subtended by the central angle theta. Find the missing quantity. Round answers to 3 decimal places. So in part A, the circle that we're dealing with has a radius of 3 meters. The central angle theta we're interested in is 120 degrees, and we're trying to calculate S, the arc length. All right, it might be helpful to kind of draw what's going on just to have a visual. So I'm going to go ahead and draw my circle. Okay, so I'm going to put a circle here. See if we can get this to draw. Ooh, that is not a circle. All right, it's looking better. Okay. There. All right, so we've got this circle, and I'm going to go ahead and draw in a central angle. So I'm going to put the vertex at the center of the circle, so maybe right about here, okay? And then we'll put one of the rays of our central angle, okay? So maybe right here, okay? And I am just going to eyeball a 120 degree angle. So let's see here. So here's one ray, and then let's draw in the other ray. So 120 degrees is somewhere probably around right here, maybe. Okay. All right, so here's your central angle, theta. Okay. Here it is. And remember, this is a positive angle we're dealing with. So if you're going from the initial side of the central angle to the terminal side, we're moving in a counterclockwise direction. So this is going to be 120 degrees there. Okay. And what else do we know about the circle? We know that the radius is 3 meters. So I'm going to go ahead and notate that. So remember, the radius is the distance from the center of the circle to any point on the circle. So this distance is a radius of 3 meters, okay? That's also equal to this length right here, okay? Those are both r, okay? So we are trying to find the arc length S, okay? So remember, now that we have our visual, okay, what's going on here? Well, you've got this central angle, okay? And what happens here is the rays of this angle, they intersect the circle in 2 spots. So like right here and then right here, okay? And the angle is in between. So the arc length that you're looking at is the arc length that's kind of intersected. That you have this angle come in and it intersects the circle, and this is the arc length that's kind of trapped by that angle. Okay, so you're trying to figure out how long this curve is. Okay, because that's kind of the part of the circle that's opposite the 120 degree angle. Okay, so that's going to be our S, okay, which is the length of this yellow piece. If remember, I always tell you to think of arc length, think of the circle as being made of a string, okay? And then if you snipped the string at the intersection point, so where I have the 2 little blue X's, and then you took the yellow piece of the string and you stretched it out, and you made a straight line out of it, and you laid it against a ruler and you measured how long it was, that's how long the arc length would be, okay? So we're trying to figure out the length of this yellow piece, okay? We know how to calculate arc length. We know the formula is S is equal to the radius times the angle theta. Okay, but remember, the angle theta has to be measured in radians, and it's given to us in degrees here. So we're going to have to convert 120 degrees over to radians before we plug into this formula. Okay, so I'm going to go over here on the side, and I am going to convert 120 degrees into radians. Okay, so we just did a whole bunch of examples of converting from degrees to radians and vice versa from radians to degrees. So we're starting here with 120 degrees. So remember, we're going to have to multiply by a conversion factor. We are trying to get rid of degrees. So since we have degrees in the numerator, we are going to put degrees in the denominator, and then radians will be in the numerator. Okay, so that way you'll have degrees in the top, degrees in the bottom. They'll cancel out and leave you with radians. Okay, so remember your conversion factor. Okay, you're multiplying essentially by 1. Okay, so we know that 180 degrees is equivalent to pi radians. Okay, so we just need to multiply this. You can think of the 120 degrees as being over 1, so now you're just multiplying two fractions. So we're going to multiply across the top and across the bottom. Okay, and again, you have degrees in the top and degrees in the bottom. Those will cancel out. So if you multiply across the top, you're going to get 120 times pi over the bottom will be 1 times 180. So 180, and you're left with the units of radians. Okay, this simplifies. Oops. This simplifies so you can reduce the 120 over 180. Both of those numbers are divisible by 60. So 120 divided by 60 is 2. So you'll have 2 pi in the numerator. And in the denominator, 180 divided by 60 is 3. Okay, so there you go. Okay, 120 degrees is equivalent to 2 pi over 3 radians. Okay, so now we can go back to our formula and we can plug in this angle. Okay, all right, so we're going to get the radius, which is 3 meters. Okay, and I'm going to go ahead and put the units here. 3 meters times 2 pi over 3 radians. Remember, radians, you can write radians, but essentially radians are unitless. Okay, so there we go. So we just need to multiply these numbers together. Okay, if you notice there's a 3 in the numerator and then a 3 in the denominator, those cancel, and so you are left with an arc length of 2 pi 2 pi meters. Be careful with the units here. Okay, so yes, we know, you've kind of got radians on the brain here, but remember, you're calculating an arc length, and so arc length is going to have the same measurement as uh, as the radius, okay, because you're calculating a length here. So it's going to be 2 pi meters, okay. So if you read the directions carefully, it says to round your answers to 3 decimal places. So this 2 pi is an exact answer, but you've got to be careful, especially if you're like in my math lab and it's asking for a specific type of answer. So if it asks you for a decimal quantity, you're going to have to give that. So yes, 2 pi meters is correct for the arc length, but if the directions are asking for a decimal answer, then you should give that. Okay, so if you go to your calculator and you do 2 times pi, remember pi is right here on the little caret button, okay, where you're raising something to a power. If you look at my calculator, you'll have to figure out where pi is on your calculator, but above this little power button, I have a pi in blue, which means I have to do second pi to bring it up, okay, and then that'll give me the decimal expansion, and we're rounding to 3 decimal places here. So remember, when you say 3 decimal places, that means 3 places after the decimal point. Okay, so we've got 2, 8, 3, 1. Okay, so if you look at that 1, okay, because we've got 2, 8, 3, and then the 1 means we should, keep the 2, 8, 3 the same. We're not going to round up. Okay, so our answer here is going to be 6.283 meters. Okay, and look how I notated this. Okay, the exact answer is 2 pi meters. Okay, and then when you do the decimal and we round it, it's an approximation. So I changed from an equal sign. The exact answer has an equal sign because it's exactly that. And then when I move over to the decimal that's rounded, I put approximately because that's an approximation. Okay, so that is the length of that particular arc length there. Okay, all right. In part B, if we move on to that, this time we are going to be calculating the central angle theta. Okay, so what we know about our circle in part B is that the radius is 6 feet and the arc length is 8 feet, and we're trying to calculate theta. Okay, so again, if you want to, you can do a visual and draw a circle here. Okay, it's a little trickier to draw the circle here because we don't have the angle. So you're just gonna have to kind of put an angle in, not knowing what it is. Okay, so I actually cannot even draw a circle at the moment, so give me a second here. So let's see here. Okay, you know what? I may be drawing a circle by hand here. It just doesn't want to move here. Okay, there we go. Okay, so here comes our circle. And like I said, we don't know what the angle is. That's what we're trying to solve for. So we're just going to have to kind of make something up here. All right, so we've got to put our central angle in. And so let's go ahead and put one of the rays in. Okay, its center is, the vertex of the central angle is at the center of the circle. And then we're just going to have to make up an angle somewhere. I don't know. The other angle was obtuse. Let's make this one acute. We don't know what it is. Okay, so you're just going to have to deal with it until you figure out what it is. Okay, so there's our central angle. We don't know what the angle is. That's what we're looking for. Okay, what we do know is that the radius is 6 feet. Okay, so the distance from the center to any point on the circle is 6 feet. The other thing is we know the arc length, okay? So however big this angle is, okay, it is going to intersect the circle, and you're going to look at the curve traced out by this particular angle that we're looking for. So I've highlighted the arc length right there in yellow, and that is what we know that length of this yellow piece is 8 feet, okay? So we know S and we know R, and we're trying to calculate the angle there. Okay, all right, so again, we can use our formula for arc length. S is equal to the radius times the angle. Okay, so we know the arc length is 8, so we can plug that in. And we know the radius is 6, we can plug that in, and that's going to allow us to solve for theta. Okay, so go ahead, if we want theta by itself, since it's multiplied by 6, we're going to divide by 6. Whatever you do to one side, you have to do to the other side. Okay, so that's going to tell us that theta is 8 over 6. Okay, and then theta, you can reduce the 8 over 6. So both of these guys are divisible by 2. So 8 over 6 reduces to 4 over 3. Okay, and so you're probably like, oh, that's a strange angle. Okay, but remember, this angle comes out in radians, because when you're dealing with S equals R times theta, theta has to be in radians. Okay, so it is actually, the angle theta is 4/3 radians. Okay, so that is the exact answer. Okay, so I'll go ahead and put, if you're dealing with radians, we don't usually write radians are unitless, but you can put radians if you want to kind of emphasize that this is a radian number. Okay, as far as the decimal goes, because the directions do ask for a decimal approximation, you can go back to your calculator and put in 4/3. Okay, round it to 3 places after the decimal point. That's going to be 1.333. Okay, so we can say that theta is approximately 1.333, and that's in radians. Okay, so either way you want to look at it, we've got the exact answer there in the decimal approximation. If you know, we're just not used to radians yet. Okay, it takes some time to get used to. So if you really wanted to visualize how big this angle is, you could convert it back into degrees just to have an idea, a better idea of how big this angle is. Okay, so I'm actually going to do that just so we have an idea of how big this angle is. Okay, so I'm going to go over here. Okay, and I'm going to do this conversion back to degrees, I'm going to use the exact answer for the angle here, 4/3 radians, instead of the decimal approximation. So if we're converting back to degrees, okay, we know we have 4/3 radians. Okay, so we're going to have to multiply by our conversion factor. We want radians to go away, so that means in our conversion factor, since we have radians in the numerator, we're going to put radians in the denominator to make it go away. And we'll put degrees in the top, okay, because that's what we want to be left with. And then multiply essentially by 1. So your conversion factor is that we know that 180 degrees is the same thing as pi radians. Okay, all right, so what we can do here is we can just go ahead and multiply our numbers together. Okay, so this is actually a fraction, so 4/3, so you can just multiply across the top and across the bottom. Okay, so this is going to be 4 times 180 over 3 times pi. Okay, and the radians will cancel and leave you with degrees because you have radians in the top and radians in the bottom. Okay, we're going to have to go to the calculator to figure out what this is. So we need to do 4 times 180 over 3 pi. Okay, so let's go do that. So I'm going to do 4 times 180 divided by 3 pi. Okay, and I'm being really careful here. I'm putting the numerator in parentheses and the denominator in parentheses just to make sure that the calculator calculates this correctly. Okay, so there's your decimal approximation. Okay, this is going to be a decimal degree answer. Okay, if we round this again to 3 places after the decimal point, this will be 0.394. Okay, so our angle that we're dealing with is about 76.394 degrees. Okay, so this is approximately 76.394 degrees. Okay, so there you go. Okay, we've got an exact radian measurement, which is 4/3 radians. That's how big the angle is. We estimated that, we approximated that. We have a decimal radian measurement for the angle, and then we also converted it over to degrees because we're just used to dealing with degrees and it's easier to visualize in degrees. Okay, so we were right when we guessed it is an acute angle. Okay, about 76.394 degrees.